Okay, hi everyone. Welcome to the exercise class. Let's start. So today we're going to discuss two exercises, um, which are in this week's exercise sheet. So the first concerns the notion of counterfactuals in classical epistemic logic, um, because as we noticed, there was some confusion about like how to use them and what exactly we mean by counterfactuals. And second, we will look at von Neumann measurements, or repeat the notion of the repeat the notion of von Neumann measurements, and also see um, how the notion of weak measurements arises from it, which will to some extent help us to deal with the counterfactuals arising in thought experiments and quantum mechanics. Okay, so let us start with counterfactuals. So let us forget for the next 15 minutes or so about like quantum mechanics and just focus on kind of epistemic logic, or in other words, on logic in which we use our knowledge about the world. So, counterfactual statements or counterfactual modalities are the statements about what is not, um, but could have been. So, for example, for example, so essentially these are the statements which answer the question, what if? So, if it rains today, then I'm taking my umbrella with me. So this is an example of counterfactual. Or for example, if there was no pandemic, we would have this class in person. And both of these statements are certain. So I know that if something happens, like for example, if the pandemic was not here, then unless there would be some zombie apocalypse or something like that, this class would take place in person. Uh, One can ask like whether uh it's reasonable at all to kind of consider the possibilities or modalities which actually don't take place. Of course, there is a lot of philosophical debate on this. However, like we can clearly see, and we'll see in the examples we'll consider today, that actually this is a very natural way of thinking. So I'm like, if you look at it, if you look for example at fiction, then a lot of fiction just explores this question of, oh, what if um I don't know, there were aliens on the moon, or what if the Second World War would go differently, and so on. And this is following that. This is also an argument, as we saw in Hardy's paradox, and as we will see today in the lecture in Frauchiger-Renner paradox. Um, these types of arguments are also used in theoretical science, specifically in the thought experiments. We also use this argument in ordinary life, or so I'm sure that everyone uh would kind of had this way of thought of, for example, yeah, again with the rain or umbrella, or you're considering whether you want to go to the party or not, and then you're like, oh, actually my ex is going to be on a party, so I'm not gonna if that person is going to be there, I'm not going. I'd better sit home and read a book. And generally these are the statements which express a particular logical inference. So from A it follows B. So for example, no pandemic, classes in person. And importantly, we can assess the truth value of this statement independent of whether the initial condition of this statement holds or not. So like, I'm not sure if the pandemic is here or not, but if there would be no pandemic, then the classes would be in person. And one way to see how this is used in classical settings is to consider several logical puzzles. And today we'll consider, I'll go through one, then I'll briefly explain the other one, and then I hope you will get the idea of like counterfactuals or understand them better. So the first, kind of the first logical puzzle is called, three logicians are ordering a beer. So let me switch to this. So these are just the slides from a presentation I was making some time ago. So here they come in useful. So three logicians walk into a bar, and keep in mind that these are logicians, so they understand all of your questions quite literally. So say that the first is Alice, then we have Bob, and then we have Charlie. And the bartender asks them, does everyone want a beer? And then the following scenario ensues. So the Alice, the first logician, answers, I don't know. The second logician, Bob, also answers, I don't know. And the third logician answers yes. And everybody happily gets a beer. So the question here is, how did the third logician, Charlie, come to this conclusion that everybody wanted a beer? And let us put ourselves kind of to analyze this puzzle, let us put ourselves like in Charlie's perspective. So suppose that you're Charlie, and then you hear Alice answering, I don't know. So the question, just to remind you, was, does everyone want a beer? And from Charlie's viewpoint, it's clear that if Alice didn't want a beer, then this would, from this, it would follow that not everyone in this group would want a beer. And so Alice could have just answered no. But instead she answers, I don't know, which means that Alice actually wants a beer, but she doesn't know if Bob and Charlie want a beer as well. So she cannot answer yes to this question. Okay, so kind of from this reasoning, Charlie has concluded that Alice actually wants a beer. Then with the Bob, the same situation happens. So if Bob wouldn't want a beer, then Bob would have answered no. However, Bob answers, I don't know, which means that actually he wants a beer, but is not sure if Charlie wants a beer as well. And so in the end, we come to the answer that Charlie has to give, and having analyzed the Alice's and Bob's points of view, we can say with certainty that both Alice and Bob want a beer, and Charlie also wants a beer. So he can just answer with certainty, being certain that everybody wants a beer, and orders a beer for everyone. So you see that, like in this reasoning, we were reasoning from the contrary in a way. So when we were thinking about like whether Alice wants a beer or not, we first assumed that she wouldn't want a beer, and then we arrived to the conclusion that if she wouldn't want a beer, then she would answer no. But this didn't happen, which clearly means that she wants a beer, and so on. So in a sense, we are putting ourselves in someone else's shoes and reasoning from their perspective, and then kind of using this counterfactual reasoning, we arrive to the conclusion. Okay, so this was an example with three logicians who successfully order a beer. So here, let me just market. So here we use the counterfactual, as in if Alice didn't want a beer, from this it would follow that Alice says no. And because she doesn't say no, but she says, I don't know, from this it follows that Alice wants a beer. So essentially the second statement here is just a negation of the first statement. Okay, so this was kind of an easy example of a logical puzzle which can be solved using this first point is the reasoning from the point of view of these agents who use their knowledge to make conclusions. And second, like reason using this counterfactual statements. Okay, so the second puzzle that we're going to consider has to do with not exactly counterfactual reasoning, but it also touches things like decision theory, and also explores how exactly we assign probability and why these things can be seen as subjective in some sense. So the second kind of this epistemic logic paradox that we're going to consider would be the sleeping beauty paradox. So the sleeping beauty paradox, as I said, it's a paradox in decision theory. And it goes as follows. So we have the main character, which is the sleeping beauty, and sleeping beauty undergoes the following experiment. So on Sunday, she's put to sleep. And during the experiment, which goes on for several days, she's woken up once or twice. Then she's interviewed after she's being woken up, and then she's put back to sleep with a sort of amnesia-inducing drug, which completely wipes out her memory about whether she has awakened or not. So experiment, awaken once or twice. Interviewed. And then put to sleep. So maybe I say it like this, like memory wiped. Put to sleep. Okay, so this is a process that our subject undergoes, namely Sleeping Beauty. But we are the experimenters, and we have to choose somehow whether we will awaken her once or awaken her twice. So as an experiment, we toss a fair coin. A fair coin is the coin which, if we toss it, we get tails and heads with the same probability, which is 1/2. And we choose out of two options. So if we get heads, we wake up, we awaken our subject only on Monday. And if we get tails, then we awaken our subject on Monday and Tuesday, so twice. And an important assumption again is when the Sleeping Beauty wakes up, she doesn't have any idea which day of the week it is, or whether it's the first time she's been awakened or the second time, because her memory is wiped. And then each time during this interview phase, she's asked the following question. So what is your credence? Now for the probability that coin landed heads. So credence here, yeah, maybe I'll just say, what is the credence for the event that coin landed heads? So the credence here is essentially the degree of belief, or kind of the probability that you would assign to the event. Of course, this could be subjective. Like, for example, like an example of why this is different, why this can be understood differently from just the fair coin toss probability is, like, for example, if you look at the weather forecast and it says in the weather forecast that it is raining with 50% probability, but then you kind of have access to a window and you look out of the window and you see that the drops are falling outside. So unless it's your neighbor who decided to dispose of the water somehow, this is most probably rain. So in a sense, though the weather forecast tells you that it is raining with 50% probability, you having the kind of the information, the knowledge about, which is of course subjective, but still your knowledge about some droplets outside your window, you can conclude that it's probably not my neighbor disposing of the water upstairs, but it's probably raining, let's say like with 90% probability. Okay, and so essentially this is what the Sleeping Beauty is asked, as in like which probability you would assign, like how probable it is that the coin landed heads, or the same as how probable it is that this is the first time you're awakened, like the first and only time, because the heads correspond to one awakening on Monday. And so now the question is that assume that you are the Sleeping Beauty and you have to answer this question. And actually, the answer to this question is a subject to an ongoing debate. And there are two ways, like two different numbers one can come up with. Here I'll briefly sum up the arguments, and I'll leave you to think a bit about it in the exercise sheet and after the lesson. So there are essentially two factions by which the people are grouped by the answer to this question. So the first faction are called the thirders. And the thirders think in a following way. Okay, so suppose that I'm the Sleeping Beauty, then there are kind of three, and when I wake up, I have no idea which day it is. I also have no idea which, like whether the coin landed heads or it landed tails. But I know that there are three options. So three options being that the coin landed on tails and it's Monday, The second option is the coin landed on tails and it is Tuesday. And the third option is the coin landed on heads and it is Monday. Yeah, and since I don't have like any other additional information, what I can only do is I say, okay, actually, all of these three probabilities, all of these three events are equally probable. And so I assign to each one of them the probability 1/3. And so in this case, the probability of the coin landing on heads is 1/3, and the probability of the coin landing on tails is 2/3. Okay, and the second, so this is one way to answer this question. The second way is the way of the faction, which are called halfas. And here, us being Sleeping Beauty, we can reason in the following way. So we know that before the experiment, the coin is fair, right? So, which means that heads is with probability 1/2, and tails, the event of obtaining tails, is also with probability 1/2. And then when I wake up on whatever day, actually me as a Sleeping Beauty, I have no other self-locating information. So here the idea is that I shouldn't update that probability for the fair coin toss. So in this sense, we keep the probabilities the same. Yeah, we keep the probabilities the same as like before the experiment, just for the toss of the fair coin. And so there are different stances on this, which I'll mention in the solutions next week, but which I'll post next week. But but I just bring to your attention, there are these two different opinions. There is no consensus. And one can see and analyze which assumptions go exactly into like being a thirder or being a halfa. But I mostly will encourage you to first think about these two ways to assign probabilities and kind of which one you see as being more reasonable than the other. But I think like this that this paradox shows very like it has two facets. So first, we again have a reasoning agent, which kind of thinks about different possibilities or modalities of the world that they're living in, or about the coin toss. And the second part is it highlights that actually the assignment of probabilities is not a very kind of intuitive action. So depending on your initial assumptions, one can assign probabilities or degrees of belief in a different way. So if we really go and think about what probabilities mean, then kind of course there is a statistical way of looking at the probabilities, but there is also this way of kind of asking yourself or asking the Sleeping Beauty which probabilities they assign to different events. So I think it also highlights this kind of interpretational issue of probabilities. There is a question. So the question is, isn't this very much like the Monty Hall problem? Yes, exactly. This is one of the Monty Hall problem is kind of in the same um, set of problems exploring this assignments. Okay, so we had a nice detour.
I'm sorry.
Yeah.
Why can't we look at the extreme case where like tails would mean that we wake her up 7 times, and or like multiple times? Then it would be like obvious to me that the thirders are right or not.
I mean, there is I'm not sure I quite understand your question, because like we're not trying to prove what which point of view is right. Um, we're just highlighting these two ways of looking at at the modalities that you're in.
Um, okay. Yeah, I was just thinking like if you make the setting somewhat different, like for example, when you have tails, then you wake her up 7 times. Um,
Mm-hmm.
then it kind of makes sense that the Sleeping Beauty would be wake not more times when it's tails, so like the probability of having tails is bigger. But like you're saying, it's a matter of perspective here.
Oh yes,
But
exactly. Because I mean, when you ask this question, actually you cannot really you as a Sleeping Beauty, you cannot really justify kind of statistically justify your answer, because you forget every time, right? So it's more of an exploration of what answer you have to give like right now. So in a sense, when if you say, let's say that we have the situation when indeed, like if the tails if we get tails, then she's awakened 7 times, then I guess like each of these events that like from the if we consider the thirder's perspective, then each of these events would be assigned the probability of 1/8, because there would be like 8 different versions, right? uh
mm,
yeah, and then you would say, okay, fine, the probability of heads is just like 1/8. But the point is, like, this is like one time probability assignment, so uh it's kind of not about proving the point statistically. Like with a for example, with a fair coin as a system, you can always prove whether it's fair or not statistically, because you can just toss it, say like 1,000 times. If you get like around 500 times um, heads and around 500 times tails, then you can with good yeah to be, you can be almost certain that this coin is fair. However, this is a bit different kind of probability, thinking about probability, than here. So here you just kind of have this particular knowledge about the situation, and then you're asked to kind of assign the probability on spot.
but you can do the experiment, right? I don't see how this is a matter of perspective. Like I don't see the difference yet.
Okay, so yeah, maybe we can discuss it after the exercise class.
Yeah, sure. Yeah, let's do that.
Um, okay, so now let us turn to the more quantum mechanical consideration. So we'll talk about von Neumann measurement, and we see how it relates to so-called weak measurement. Okay, and so first a bit of motivation. So as you've seen in both like this pigeonhole quantum pigeonhole principle, which does not align with our classical intuition about this Dirichlet principle or pigeons, or like as you've seen in a lecture with the Hardy's paradox, we use the counterfactuals to kind of to show some inconsistency arising. The problem with the counterfactuals, or like one objection against counterfactuals that we can make, is that actually we're just to say that, oh, we're talking about the results of the experiments which are actually not carried out. So because, like, if you remember, we are making statements like, oh, if I measure this system in this basis, then I would get this result. But it does not really but making this statement does not really mean that we actually measure the system in that basis. It's more like this: if I do this, then I would get this result. And of course, again, one can say that if there is no measurement carried out, there is no point in making such statements. Well, here we can actually use state that this objection is of no consequence to us, because what we can do is, fine, we cannot make these measurements because they would disturb the system. However, we can make measurements which would minimally disturb the system using the additional system, such as memory or measurement device, and then kind of refer to the values that we get out of this measurement device, and still, in Hardy's case, still arrive to contradiction or like weird results. So, but before, and these measurements are called weak measurements because we use other system to weakly disturb the measured system, and still, even though the interaction is weak, we are still able to extract some information about the measured system. So, but before we go to this weak measurements, let us discuss von Neumann measurements, or von Neumann scheme of the measurement. And the motivation for the von Neumann scheme of the measurement is that, so suppose that we are measuring some quantum system and we obtain a certain outcome. And here we can go down kind of the line of thinking that you should already be used to by now, as in thinking, oh, I get the outcome. The outcome is some information. Information is physical. So outcome, information, physical. And hence, it has to be described as some physical system, or we can describe it as some physical system. And this physical system, it is called measurement device, or memory also. And and this essentially, and this idea of measurement as measuring a system via interaction with this measurement device and writing down the result to the measurement device is the von Neumann measurement. So it's measured system plus measurement device. So for example, just as a very rough example for the discrete case, so suppose that I have a system S, which I want to measure, and it's a qubit, and it is in state plus. So 1/2 0 plus 1. And then I have the system M, which is initially in a state 0, let's say. Then I can, how do I carry out the measurement process? So I measure the system M, and then I write down the result to the memory So I measure the system S, and then I write down the result to the memory M. And I can do this by, for example, applying a C-node gate. And then I would end up with the state where we have that the system M is correlated the system M is correlated with system S. Moreover, like in this example, it's kind of a coherent copy. So here, if I measure the system M in a state 0, then S is also in a state 0. If I measure in a state 1 the memory, then the system S in a state 1. But this is kind of a strong correlation, right? Because here, by measuring the system M, I collapse the system S in the corresponding state 0 or 1. So these are the discrete systems. Generally for continuous systems, and you actually already seen this interaction before, in some way for the clocks, we can describe this interaction by the interaction Hamiltonian H, which we would write as G of t, AS, or tensor product PM. And here the idea is, given this interaction Hamiltonian between systems S and M, where S is the system that we want to measure and M is the measurement device, we can measure the operator A on the system S, and couple it to the by having the momentum operator here, we can couple it to the position of the system M. So essentially, act of this Hamiltonian will result in different eigenvalues of S being coupled to the wave function, to the part of the wave function of the system M, which would be shifted exactly proportionally to the eigenvalue of these operator. And G of t here, the same as in the clocks case that we were considering, it just corresponds to or describes the switching this interaction on and off. So it's just, you can actually even think that it's constant. So it has only support between the initial time and the final time of the interaction. Okay, and so the idea here is to take this Hamiltonian, apply it to the initial state, which is just the tensor product of the states of the system and the measurement device. And then RU is this. And so if we calculate this this unitary, let me quickly do it. So if we see this unitary, then we just write it out as Taylor series. So hi to the power n would be, so G, I'll assume that G of t is just G, the constant here. And it's only from time ti to tf, so acting from the initial time to final time. So I have G to the power n, AS to the power n, PM to the power n. Okay, so then what exactly is AS? So AS can be written out as a operator diagonal in its eigenbasis with the eigenvalues AI. So this is the operator that we want to measure on the system S, right? And because it has this form, because it's diagonal, it's essentially, we can easily see that the nth power of it corresponds to each of its diagonal elements brought to the nth power. So we can substitute it in our expression for the unitary. So we have g to the power n sum over I ai to the power n ai by pm to the power n. Then I exchange the order of the sums, and what I get is the following. So I have sum over I ai tensor product sum over n minus it to the power n over n factorial g to the power n ai to the power n pm to the power n, which basically means that each ai is paired to the exponential e to the power minus I t ai pm. And if you recall this expression from quantum mechanics course, then this expression is actually just the shift operator for shifting the position. So acting on x, where x is some position, then this brings it to x plus, I forgot g here. So it's AITG. And essentially then if we take our initial state, where we have the position of the measurement device m somehow distributed in space according to its wave function psi of x, we see that kind of for each separate kind of projection on each AI, we will have that the wave function is shifted by a different amount, because here we have an expression, like a shift expression, depending on the eigenvalue AI. Okay, and so in the exercise, you have to write this out for psi of x, so the wave function of the measuring device being a Gaussian, and see how how essentially you would have several Gaussians but just shifted with respect to each other. And then the idea of kind of going from this to the weak measurements is to note that actually we can tune the strength of the interaction by tuning this parameter here, g. So the less g is, the weaker the interaction is. And so weaker in a sense that the peaks of the Gaussians, which are superposed, would be closer and closer to each other. And then one can show that like in the limits of this weak interaction, the approximate final state would be a Gaussian, but which would be centered around kind of the mean value of the of the measured operator A. And additionally, if we also add pre and post selection, so if we like we did in a Hardy's paradox and also in this pigeonhole principle consideration, so if we pre-select on a state psi and post-select, post-select on a state phi, then the approximate final state would be a Gaussian centered around GAV, where AV is so-called weak value of the operator. And coming back to the Hardy's experiment, so sorry if it's all was a bit rushed. We'll also talk about this pre and post selection in the next exercise class and its connection to the weak values. But here the idea is that having this weak values, we can modify Hardy's experiment such that we would get the values which we consider counterfactual as not hypothetical counterfactual values, but as actual measurement results of these weak values, is here. But even having this weak values by this kind of indirect, almost non-disturbing measurement on the system, we can still acquire very weird and unintuitive statements about the setting. But this we'll look at in the next exercise class. If this description of the measurement was a bit rushed, I believe that Lydia will also repeat it to some extent in the lecture. So yeah, I hope this was more or less a good introduction to the topic. Okay, this is all I had for today. So yeah, feel free to ask questions.